Hello, and welcome to Settle the Stars. Episode 15, Uranus and Neptune, the Newcomers. Hey folks, this is Alexander Wynn. Today we begin our journey extremely far from home, continuing our journey farther out into the solar system as we visit the last two planets on our list, Uranus and Neptune. These remarkable planets drift through the cold, dark edges of our solar system, an area of space as mysterious as it is distant. Today we'll explore the surprising differences between these sister worlds and learn about the important discoveries they have prompted in the scientific community, even from a great distance. Now that we have Saturn, with its rings and its army of moons, behind us, ahead we can only see the darkness of open space, crowded with distant stars and galaxies. These two ice giants orbiting in the blackness beyond are generally too far away from Earth to see with the naked eye, so they don't share the deep-rooted cultural history of their closer and brighter cousins. Uranus, the closer of the two, may have been observed as a star as early as 128 BC by the Greek astronomer Hipparchus, but the earliest confirmed sighting is claimed by John Flamsteed in 1690. The first of England's prestigious Astronomers Royal, Flamsteed believed Uranus to be a star, but the distance helped ensure the planet was only sporadically observed, fewer than 20 times by Flamsteed and his French colleague Pierre-Charles Lemonnier for the next 100 years. In 1781, accomplished musical composer Sir William Herschel found time while serving as the director of the Bath Orchestra in England to observe the planet from his garden. By gradually increasing the power of his telescope with various lenses, Herschel was able to make an important observation. At greater power, the diameter of the object appeared to increase, while the background stars remained unchanged. Herschel knew this must mean that the object he was observing was much closer than the background stars, which are so distant that no modification of his telescope could resolve. Herschel hypothesized that the object he was observing at the time was a comet, objects he was well known for identifying and observing. But within 2 years, the scientific community had accepted its status as a new planet beyond Saturn. As follows many important scientific discoveries, debate ensued for the next 70 years to decide a name for the planet. Johann Elert Bode, who would use his own observations of the planet to determine its orbit, helpfully suggested the name Uranus, in keeping with the existing naming convention of the other planets. He chose the name after the Greek god of the sky Uranus, father of the Titans and husband of Gaia. Eventually, the name beat out the other competing titles, in part due to the help of Bode's peer at the Royal Academy, Martin Klaproth, who named his own newly discovered element uranium in support of the choice. Although the name was finally settled, Uranus continued to mystify astronomers for another 200 years until optical technologies caught up with the challenge of distance. Over that time, bits and pieces began to emerge that surprised many scientists, including the unique characteristic of alternating through periods of relative brightness and darkness during its 84-year orbit. The cause of the anomaly shocked many scientists. The planet is almost completely tilted on its side, orbiting the Sun with its north and south poles skewed out to the sides, with its rings and moons circling up and around the planet's reclined equator. The variations are caused by the relatively light poles, or dark equator, being visible at any given time during its orbit. It wasn't until March of 1977 that it was even confirmed that Uranus has a faint system of rings. Herschel had reported observing rings in 1789, but many astronomers believed the rings would have been too dark to observe with his equipment. But by August of 1977, the Voyager 2 spacecraft was launched, and scientists would get their once-in-a-lifetime opportunity to analyze the planet up close. Among Voyager 2's busy itinerary was a flyby of Uranus, with the closest approach on January 24, 1986, almost a decade after launch, just 81,000 kilometers above the atmosphere. By the time it reached the planet, Voyager 2 was about 1.8 billion miles from home, but still going strong. Powered by heat generated by the radioactive decay of plutonium oxide spheres, and equipped with an array of sensors and cameras, Voyager 2 produced enough data to keep scientists busy for decades, and boy has it ever. Images received from the spacecraft show just how on-the-nose Bode was when he proposed to name the planet after Uranus, the ancient Greek god of the sky. A rich sky-blue atmosphere surrounds the planet, obscuring almost any details or characteristics. Data from the Voyager 2 indicate that the color is due to the presence of methane, the primary component of the planet alongside hydrogen and helium. Although the atmosphere surrounding the planet contains much more helium and hydrogen than methane, the trace amounts are enough to impart the characteristic pastel blue coloration. In contrast to the dynamic and turbulent cloud bands of Jupiter and Saturn, the occasional white methane cloud observed in the atmosphere of Uranus was a rare sight, and only once observed before the flyby in 1986. Images from Voyager 2 showed a grand total of 10 clouds planet-wide. It also revealed a faint collar of lighter clouds surrounding the southern pole of the planet, which was thought at the time to be part of a symmetrical banding around the planet at the opposite poles. Much to the frustration of scientists back on Earth, the flyby of Voyager 2 coincided with the middle of summer, which meant only the southern hemisphere was exposed to the light of the sun due to the extreme planetary tilt. However, as new images from Hubble arrived after the equinox in 2007, a surprising pattern of seasonal shifts was observed. As the planet's north pole emerged into the sunlight, a collar gradually appeared, and the southern collar disappeared almost entirely as the seasons shifted. It's thought that these collars are the result of thickening methane clouds and haze caused by the increased sunlight, which could explain why the switch occurs during the seasonal change. Other atmospheric observations were noted as well, from wind speeds to cloud shape and composition, suggesting an unexpectedly drastic seasonal weather change dynamic. Scientists believe these drastic seasonal changes are the cause of increased weather activity, which leads to the formation of swirling storms like those observed on the other outer giants. One such, named the Uranus dark spot, was observed during the equinox period in 2006 and measured about 2,700 kilometers at its widest, and crawled through the clouds at 43 meters per second. A small storm compared to the mighty tempests of the other large planets, but a big event in the otherwise empty skies of Uranus. But empty skies don't mean the air isn't moving. Wind speed can vary depending on where you are on the planet and what season it is, but generally the breezes are around 50 to 200 meters per second. In an effort to answer the question of empty skies, scientists looked for clues in some of the other data provided by Voyager 2. Astronomers expected Uranus to be cold, but they didn't actually expect it to be this cold. Only negative 353 degrees Fahrenheit on average, and as low as negative 371 degrees has been recorded, making Uranus the coldest planet in the solar system, even colder than Neptune, which is orbiting much farther out into space. Compounding the mystery is that the inside of the planet is also a comparably frigid 8,500 degrees Fahrenheit at the core. That may be more heat than you or I could take, but after exploring the center of Jupiter at 43,000 degrees, or even Earth's core at 9,400 degrees, you might have to ask for a blanket. Surrounding the core is a mantle of frozen water, ammonia, and methane, with some recent studies suggesting that the extreme pressures could cause carbon atoms to form oceans of liquid diamond, with huge diamond bergs floating around, pelted by sheets of diamond hail. But guessing the internal composition of the planet unfortunately doesn't offer much in the way of explanation for the relatively calm exterior of the planet. A theory was proposed to explain some of Uranus's strange outward characteristics with a catastrophic and yet relatively common astronomical event, a massive collision. Sometime early after formation, it's hypothesized that a huge object collided with the young planet. The impact would not have been a direct hit, but off-center and powerful enough to knock the planet sideways into its current axial tilt. Such an event would have ejected millions of tons of ice and dust into space, which could also explain the ring and moon systems we can observe even today. But what evidence can scientists use to corroborate the theory? One piece of evidence favored for this task is to map the magnetic field. Among Voyager 2's impressive array of gadgets was a fluxgate magnetometer, which measured the magnetic field strength and direction of the planet as it flew by. Unfortunately, or maybe fortunately, as a curious scientist would say, the readings around Uranus were unexpected and created more questions than they answered. The magnetic field surrounding Uranus is not aligned with the geographical axis of the planet, tilted almost a full 60 degrees away from it. Additionally, the center of the magnetic field, called the magnetic dipole, is shifted from the center of the planet almost a third of the way to the southern pole. The observations made by astronomers and confirmed during the visit of Voyager 2, the anomalous axial tilt, the unexpectedly cold temperature, and the eerie lack of weather, to name just a few, have certainly established Uranus as one of the most mysterious planets in our solar system, a distinction certainly frustrated by the difficulty faced in observing a planet so far away. If only we had another example planet to observe, another similar ice giant that could shed some light on what's normal for this class of planet and what's unusual. Oh, hey Neptune, I didn't see you all the way out there. Drifting farther out into open space is the last official planet in our solar system. Sorry, Pluto. And an answer to astronomers' wishes for another ice giant specimen to observe and compare with Uranus's many quirks. It's easy to fall into the misconception that Neptune and Uranus are right next door. They may be neighbors, but they're separated by a distance of about 1 billion miles even at their closest approach, more than twice the distance from Jupiter to the Sun. At a total distance of about 2.7 billion miles from the Sun, it's no surprise Neptune evaded detection for so long. Despite likely being observed by Galileo as he studied Jupiter back in 1612, Neptune was well disguised as a background star, because coincidentally, on the exact day Galileo saw it, it was just turning retrograde and would have appeared nearly stationary against the starry background. After dodging Galileo, Neptune would orbit in peace for another 200 years without notice. In 1821, many astronomers were still fascinated by Uranus, collecting and sharing new data to build an understanding of the mysterious new planet. One such was the meticulous Alexis Bouvard, who carefully charted and published tables of the planet's orbit. As more observations were collected and compiled, discrepancies became evident between the observed locations and Bouvard's tables. Confident in his careful measurements, Bouvard theorized that an unknown force was nudging Uranus off its expected course, possibly even an as-yet undiscovered planet. With this news, an astronomer in Britain named John Couch Adams, and one in France, Urbain Le Verrier, among other rivals competing for the honor of planetary discovery, set about calculating and proposing possible locations and trajectories for the mysterious object. On the evening of September 23, 1846, Johann Gottfried Galle at the Berlin Observatory was scanning the sky at the request of Le Verrier. He recorded the first confirmed observation just 1 degree from the location provided by Le Verrier, which was about 12 degrees away from Adams' best guess. A fierce nationalistic debate erupted between the astronomers of the two nations, each claiming to have discovered the planet and proposing names. Eventually, the dispute was settled with the help of an influential third party, Russian astronomer Friedrich Georg Wilhelm von Struve. Struve supported the name Neptune, which was neither country's first choice, and before long the name stuck, and the normal squabbles of any healthy scientific community resumed. An appropriate choice for the deep blue color of the planet, Neptune was named for the Roman god of the sea, corresponding to the ancient Greek deity Poseidon. Across the globe, different nations and languages adopted their own names for the new planet according to local culture, almost always for an entity associated with the ocean. Unfortunately, discovering and naming the planet didn't make it any easier to observe at such incredible distances, and it would remain a mysterious blue dot to even the most powerful telescopes until the application of adaptive optics in the late 1900s. Any stargazer can attest to the gentle wavering or shimmering of the stars in the night sky. This twinkling effect is not caused by perturbations within the light itself, or variations in the brightness of the actual object being observed, but are in fact distortions caused by air currents in Earth's atmosphere. Some astronomers have even compared the difficulty of detailed observation from Earth to attempting to birdwatch from the bottom of a swimming pool. To mitigate these distortions, a new telescopic technology was made possible by the quick calculations of computers. By building flexible mirrors with pistons to automatically react to atmospheric distortions with fine-tuned adjustments in real time, scientists were able to minimize the distortions and obtain much finer image detail. The first scientifically useful images of Neptune weren't obtained until 1997, when this technology was applied in Hawaii. The other solution, of course, is to build a powerful telescope above the atmosphere, which is why the Hubble Space Telescope has been such a valuable asset to deep space observations since its launch in the 1990s. With these new technologies bringing Neptune into sharp focus for the first time, detailed observations began to emerge. The most striking characteristic is the planet's similarity to Uranus, both in size and in their blue coloration. Like Uranus, the color is caused by the presence of methane in the atmosphere, but for unknown reasons the color is a much darker shade. Neptune also rotates on a regular upright axis, unlike the sideways spin of the closer ice giant. The other obvious difference is that Neptune appears to have a much more active weather system than Uranus, with great billowing white cloud systems made of methane and the occasional giant storm. Several such storms have been observed from Earth, and while not as famous as Jupiter's Great Red Spot, Neptune's own Great Dark Spot, viewed by Voyager 2 in 1989, was almost as large. Several similar vortices have appeared over the past several decades of observation, and while stable in structure, they only last for a few months at a time. A reasonable observer could easily hypothesize that Neptune's great distance from the Sun, over half again more than even Uranus, and the tiny amount of sunlight it receives would mean a much colder world, incapable of supporting much atmospheric activity. But while the chilly core of Uranus only generates about 1.1 times as much energy as it receives from the Sun, Neptune remains a powerhouse, generating 2.6 times as much energy as it receives. It is believed that this surprising output of energy is responsible for Neptune's much livelier atmosphere, to such a degree that this icy world boasts the strongest atmospheric winds in the solar system, clocked at almost 1,300 miles an hour. Clues about the interior of the planet could shed some light on the reason for this additional internal heat, and thanks to Voyager 2's trusty magnetometer, scientists were able to gather some useful data. What the scientists found is that Neptune's magnetic field shares some of the unexpected quirks of Uranus's. Just like the other ice giant, Neptune's field is strongly tilted about 47 degrees from the rotational axis, and similarly offset from the center of the planet, over halfway to the surface. While interesting observations, paired with the findings at Uranus, scientists could conclude that the skew was not in fact due to the strange rotation angle of the other planet. Evidence suggests that this may be a feature common to ice giants in general, possibly because their unique interiors generate a field farther out in the mantle than the core-based fields we see in other planets. Otherwise, the interior of the planet is much like that of Uranus, with a mantle rich in water, ammonia, and methane, and varying layers of ionic fluids. Some scientists propose that the intense heat and pressure of Neptune's interior could support similar wild conditions to those hypothesized in Uranus and Jupiter, with storms of diamond hailstones. As of yet, there is little information to shed light on the mysterious discrepancies between the internal heat generated between Uranus and Neptune, but more research has been proposed to keep searching. Several missions to the outer ice giants have been proposed, some possibly launching this decade. Unfortunately, the distance and the hazards of spaceflight will make human exploration unlikely for many more years, but the rich source of helium-3 is an attractive prospect for applications in nuclear fuel, especially if spacefaring becomes more popular and a gas station at the edge of the solar system becomes necessary. It's likely that humans would first visit some of the interesting moons around the planets, which coincidentally is exactly what we'll be doing in next week's episode. I hope you've enjoyed this visit to the twin ice giants Uranus and Neptune. In our next episode, we'll take a closer look at their fascinating ring structures and moons, and what they teach us about conditions in the early solar system and how planets form. Thank you, as always, for listening. If you haven't already, be sure to subscribe so you get new episodes every week. And a quick thank you to those who have left us reviews on iTunes, Spotify, or wherever you listen. Reviews are the easiest thing you can do to help support an indie podcast like ours. So if you want to help make sure that Settle the Stars can continue our explorations for a long time to come, please give us a rating and share a few words with prospective future listeners. In the meantime, thanks again for listening, and as always, happy terraforming. Settle the Stars is a proud member of the Edgeworks Nebula, a collection of intriguing and informative podcasts from Edgeworks Entertainment.
Edgeworks Nebula.